Hello everyone. Today we're going to be learning more about the motor effect. So the motor effect is sort of demonstrated over here. It's a curious force that's experienced by a current carrying conductor when it's in the presence of a magnetic field. So we can see over here we have a pair of magnets with a north pole and a south pole and a magnetic field line in the middle, and it causes the wire in between them to move. So the cause for this is because when we have a wire inside a magnetic field and that wire is carrying a current, then that wire will experience a force, right? So we'll be learning about the strength and the direction of this force later on. The force is called the motor effect. That's what all the fuss is about. The fact that we can get electrically charged wires to move in a magnetic field means that the motor effect is very, very useful for producing movement out of electric devices, and in particular, electric motors. So the force will act perpendicular to the magnetic field and perpendicular to the direction of current. We can see that over here. That's why it's important to remember how vectors work. In this case, the magnetic field is pointing towards you because it's represented by dots. The wire is pointing towards me, or rather the current through the wire is pointing towards me. So if we need to create a vector that's perpendicular to both the magnetic field and to the wire, then it will have to be pointing up or downwards, right? So this motor effect is a three-dimensional thing. We can't really handle just two dimensions. So we can figure out the strength of the motor effect by looking at the following factors. We can look at the strength of the magnetic field, which, as you can recall, is measured in Tesla. We can look at the magnitude of the current, which is measured in amperes. We can measure the length of the wire, which is measured in meters. And finally, the angle that the wire makes with the magnetic field, which at this point you'll usually measure in degrees. Some of you might have learned about radians, which is a different way to measure angles, but you won't really need to use it in physics. So how do all of these affect the strength of the motor effect? Well, a stronger magnetic field, as you might have guessed, will mean a larger force. How about changing the amount of current? Well, once again, as you might expect, a larger current will create a larger force. If there's no current, there'll be no force. Just as if there's no magnetic field, there'll be no force. Can you imagine what else might affect it? Well, one important factor is the length of the wire. If there's a longer wire, then there'll be more of the wire to experience a force. So the total force on the wire will be greater. And finally, the one other variable in this diagram is the angle that the wire makes with the field. So if we have a wire that's perpendicular to the magnetic field, it'll experience the greatest amount of force. But if it's parallel to the field, that is, if it's pointing straight up or straight down in this diagram, then it will experience no force. So mathematically, we can write this down. We can say that force is proportional to magnetic field, current, length of the wire, and the sine of the angle. So remember, if the angle is 0 and our wire is parallel to the field, then sine of that angle will also be 0. Whereas if we're perpendicular and our wire is at right angles to the magnetic field, then sine theta will be a maximum. So let's look at an example. We'll take a length of wire, 20 centimeters long, and place it inside a magnetic field, right? The magnetic field has a strength of 50 milliteslas, or 0.05 Tesla. So what force acts on this if it's carrying a current of 3 amps, which is a fairly large current? And another thing to ask yourself might be, in what direction will it act? All right, well, we can figure this out with our formula, right? F equals BIL sine theta. So here's the equation from before. All we need to do is substitute in our numbers. So B is given here, I is given here, L is up the top, and theta is going to be 90 degrees, right? Because we've got the wire perpendicular to the field. So substituting in these numbers and remembering to turn centimeters into meters, we'll end up with an answer of 0.03 newtons. Remember that force is measured in newtons. If we look at the units of the equation, we can actually see that 1 Tesla times 1 ampere times 1 meter equals exactly 1 newton. All right, let's have another example, this time with an angle, so that we're not quite perpendicular anymore. A length of wire, this time 1.3 meters long, is placed in a magnetic field of intensity 20 milliteslas at an angle of theta equals 30 degrees. So what force does the wire experience if it carries a current of 5 amps? All right, well, once again, we can use our formula to figure this out, right? F equals BIL sine theta. In this case, theta will be 30 degrees because the wire makes an angle of 30 degrees with the magnetic field. Now, at first it might not look like 30 degrees, but remember that physical diagrams are not always drawn to scale. So we have 0.02 for the magnetic field, 5 for the current, 1.3 for the length, and sine of 30 degrees. And of course our answer will be in newtons. So this will turn into 0.065 newtons. Now you'll notice that these forces are not particularly big forces. So if we want to get a strong force acting on a wire, we need to have a large magnetic field and a large current. So let's think about the direction of the force. Remember that the direction will have to be at right angles to the other two parts. That is, it'll have to be at right angles to the current and at right angles to the magnetic field. In the previous questions, this means that the force has to be either towards you or away from you. So how can you figure that out? Well, we use the right-hand palm rule, which we can see over here. So the fingers will point in the direction of the magnetic field, right? Often the magnetic field is represented by multiple parallel lines, and so this is handy because we have multiple parallel fingers. The thumb points in the direction of the electrical current, just like the right-hand curl rule, so nothing new there. So we have a magnetic field in one direction and an electric current in another direction, and the force will need to be at right angles to both of these, so it'll have to be either up or down. And we can see here that the palm will be facing the direction of the force. So if we have a magnetic field pointing bottom to top and an electric current pointing left to right, that means that the force will be towards you. If the magnetic field is pointing in the other direction, the force will be away from you. Or if the electric current is pointing the other direction, the force will be away from you. Right? If we reverse both the direction of the electric current and the magnetic field, then the force will be in the same direction, towards you. Right? So, let's look at another example. We take a wire and lay it right to left on a table in front of us. There's a uniform magnetic field which points with crosses, which means away from you. Right? So when current is passed through the wire, does it move left or right or up or down or forward or back? Well, let's work this out. We can use the right-hand rule. Right? So let's go through it step by step. Point your fingers of your right-hand rule, not left-hand rule, towards the table. Right? That'll be the same direction as the magnetic field. So away from you. We take our thumb and point it to the left in the direction of the current. Right? So now we've got our fingers pointing in and our thumb pointing across. So what we're measuring now is the direction that our palm is facing. right? And so it'll end up facing downwards. So the force on this conductor is downward, right? Now remember, the fact that we're using our right hand and not our left is just because of how our system of lines works. If our magnetic field lines pointed from the south pole to the north pole of a magnet, because we had a different convention, then we'd have to use our left hand to figure out the direction of the force. Of course, the way our convention currently works means that we can only ever use our right hand, which, I noticed, repeated because it bears repeating, which means that you can't be writing down an answer with one hand and then checking your other hand for the direction of the force. You have to always be using your right hand to find this out. If you're right-handed, that means you'll have to put down your pen and look at your right hand to figure it out. Let's go on to some questions. Question 6. A circle of wire lies on a desk and contains an electric current circling clockwise. Let's draw a diagram, shall we? Clockwise will be in this direction. So in which direction do the magnetic field lines point in the middle of the circle? Do they point inwards towards the circle's center? Do they point outwards towards the wire? Do they point into the desk, or do they point out of the desk? So we can use our right-hand grip rule to figure out the direction of the magnetic fields around a segment of wire, right? If we have a straight wire like this, then we can use the right-hand grip rule, point our thumb in that direction, and figure out that the magnetic field lines must be coming towards us at the top and away from us at the bottom, because it'll be a circular magnetic field, right? So now let's look at this example here. If we look at the very top of the wire, we can see that that will still be the case, because this very top of the wire is like a horizontal conductor. If we look at the bottom way, we can see that it'll be the other way around. So there'll be, once again, a cross inside the circle and a dot on the outside, right? That's the right-hand grip rule. So if we do this all the way around the circle, we'll see that at the middle of the circle there's basically just a big X, right? Pointing inward toward the circle. So how do we answer this multiple choice question? Well, we can go through all the options to see why each one is wrong. If they went inwards toward the center of the circle, they would be intersecting at the center, and we know that they can't intersect. Same deal for moving outwards towards the wire. It means that the place that they started would be the middle, and they would have to intersect there. So it has to be into the desk or out of the desk. And we know that if we apply the right-hand grip rule, we can see they're traveling into the desk, right? We know it with crosses, and crosses means going inwards, away from you. Question 7. A current carrying conductor in a magnetic field experiences a force, right? The motor effect. So if the current in the conductor is doubled, but nothing else is changed, how will the force change? So what equation can we use to figure this out? That's right, F equals BIL sine theta, that new one, right? So if we have the current doubling, then that's the I and the BIL sine theta doubling, right? So how will that change the force? Well, we can see that the force will change because there's an I in the equation. We can see that the force won't disappear because the current hasn't dropped to zero. We can see that the force isn't going to get smaller, and it will in fact double. So doubling the current in the equation will double the force. Question 8. A current carrying conductor is in a magnetic field. Oh, sounds familiar. What angle must the conductor form with the magnetic field to experience the most force? So this is concerning the theta in our equation, right? F equals BIL sine theta. So what we're trying to do is make that sine theta the biggest number we possibly can. And that happens when? That's right, sine theta is 1 and theta is 90 degrees. So force is maximum where sine theta is 1 and the angle is 90 degrees. So that is, the wire has to be perpendicular to the magnetic field. Part B, what angle must it form to experience the least force? Well, it'll just be the minimum of sine theta, right? So the force will be minimum when sine theta is 0 and the angle is 0. Now if we look at what this would look like in real life, it would mean having an electric wire parallel to the magnetic field lines. So if the field lines point from top to bottom, then the current carrying conductor will also point from top to bottom. Question 9. A wire is 7 centimeters long, has a current of 4 amps flowing through it, bottom to top, and experiences a force of 0.084 newtons on it due to the motor effect. So what's the strength of the field, assuming that we're perpendicular to the field? So let's take a look at this. We have bottom to top, we have a current, which I'll mark I, our symbol for current. It experiences a force, which will be equal to BIL sine theta. Now, because we don't know the direction of the force, whether it's left or right, or towards us or away from us, we can't figure out the direction of the magnetic field, because we know that the field will have to be perpendicular to both of them. However, with this equation, even though it won't tell us the direction of the magnetic field, we can still figure out its strength, right? So how would we rearrange this? Well, it's not too hard. You can probably manage it just with the basic algebra you've learned in year 10 maths if you wanted. So we start off with F equals BIL sine theta, and we divide both sides by IL sine theta. So that it looks something like this. There's the F on top and the IL sine theta at the bottom, right? So now we have a measurement for B. Putting this equation into a calculator, we'll end up with an answer of 0.3 Tesla, which is rather a strong magnetic field. Question 10. A piece of wire with a current flowing left to right through it is suspended by 2 paper clips. The north pole of a magnet is held underneath the wire, and the south pole of another magnet is held above the wire. So in which direction do the magnetic field lines point? Well, we have south pole over here, north pole over here, and we have an electric current flowing left to right. So what direction do the magnetic field lines point in? That's right, north to south. So we can answer the question by saying the magnetic field lines here will point from bottom to top, right? So what direction will the wire move, if at all? Well, now that we know the magnetic field lines, we can use our right-hand palm rule to figure out the direction of the force. The field lines go from bottom to top. So there's our magnetic field, represented by B. And here's our wire, going left to right. So, let's use the right-hand palm rule. The current goes from left to right. The magnetic field goes bottom to top. So, the current carrying conductor will be pushed towards you. And so, that's the answer that we write down. Right? The right-hand palm rule shows us that the force will be towards you. Question 11. A length of wire perpendicular to a magnetic field is 3 centimeters long. The strength of the magnetic field is 10 millitesla, that is 0.01 Tesla. 1 amp of current flows through the wire from left to right. What is the direction and magnitude of the force that the wire experiences? Alright, so the magnetic field line flows bottom to top, and the current flows left to right, same as last time. Except now we actually have numbers, so we can figure out some quantitative measurements of the force. So the direction is found by the right-hand palm rule. Bottom to top, left to right, force is towards you. Right? But how do we find the magnitude of the force? Well, we use our equation for it. So after we've used the right-hand palm rule to determine the direction of the force, points towards us, of course, we can use F equals BIL sine theta to figure out the magnitude of this force. So B equals 0.01, I equals 1, L equals 0.03 meters, and sine theta will be 1 because we're perpendicular. So 0.01 times 1 times 3 centimeters times 1 gives us an answer of 0.0003 newtons towards us. So this gives you the sort of idea that very short wires with relatively small currents will experience. But remember, because these wires are quite small, this amount of newtons might be able to produce an appreciable difference to the wire's motion. So that's the end of the questions, which means we're now at the end of this section. So we've learned about magnetic field lines and the motor effect. The motor effect is, of course, the fact that a current-carrying conductor, when it's placed inside a magnetic field, will experience a force perpendicular to both the direction of current and to the direction of the magnetic field lines.